Hello, scientists. Today we are talking about the inner planets or the terrestrial planets, the first four planets, the closest four planets to the sun in our solar system. We will also be talking about how scientists measure distances in space, and we will talk about the inner planets themselves, obviously, and describe their properties. So to get us started, during the early 17th century, um, an Italian astronomer and a physicist named Galileo is what we usually refer to him as. He first used a telescope to observe the planets and stars. And over the years, advancements in technology led to the development of more powerful telescopes. We talked about this a little bit already um, during the 50s and 60s, 1950s and 60s. Both the Russians and the Americans developed spacecraft that carried people into space, right? We talked about the USSR being the first ones to make it into space, and then the United States was soon to follow. And then the United States are the first and so far the only country to have actually walked on the surface of the moon. Since then, however, spacecraft, even though we have not returned to the moon with human beings have not walked on the moon since then. But unmanned spacecraft equipped with cameras and all kinds of other devices have collected data about every single planet in our solar system. So even though we have never set foot on any of them, and as we go through the lesson today and next time, you'll see why there's a good reason that we haven't set foot on some of these planets. But we have sent probes and things like that to every planet in our solar system. The inner four planets, the first four planets in our solar system, are Mercury, Venus, Earth, and Mars, and that's in order, closest to farthest from the sun. We call them the terrestrial planets because they have solid surfaces, basically, rocky surfaces, terra. Um, and the next four planets are Jupiter, Saturn, Uranus, and Neptune, and we call those Jovian planets. Jovian means Jupiter-like. They do not have solid surfaces. We sometimes call them the gas giants because they are much larger and more gaseous than the terrestrial planets are. Here are pictures of Mercury, Venus, Earth, and Mars. I think they are pretty pictures, but what this picture, this compilation here doesn't do justice is the relative sizes. They're not all the same size. They are very different in size, and their distances. They obviously are never this close to one another. They are very, very far apart. Here is just an overview of some properties of the terrestrial planets. Some important things I want you to note. The orbital period for each one. Orbital period meaning how long it takes to go around the sun. What is the length of a year, as it were? We know 365 days in a year here on Earth. The closer the planet is to the sun, the shorter its orbital period, and that's what we talked about with Kepler's laws. That the closer you are to the sun, the faster you move. And then we talked about how Isaac Newton figured out why that is the case, because inertia balances out gravity. The period of rotation is how long it takes to make one spin. And you can see that Mercury and Venus take a very long time to spin. In fact, it takes longer for Venus to spin once than it does for Venus to go around the sun. A day on Venus is longer than a year, which is kind of weird. But Earth and Mars both have relatively similar periods of rotation. The mass and diameter are good measurements of size. Roughly, it's a little hard for you to read that mass column because we need to make sure we're comparing apples to apples. This is written in scientific notation, so even though they all kind of look the same, Notice these exponents, and that's really the important thing. It looks like Earth and Mars are relatively similar in size until you realize that, oh no, the mass of Earth is about 10 times the mass of Mars. So actually, Venus and Earth have relatively similar masses and relatively similar diameters. They're pretty darn close in size. Mars is about half the, really roughly half the size of Earth, and Mercury is again super rough, but roughly 1/3 the size of Earth. And then the last interesting thing I want to point out here, Venus is the hottest planet in the solar system by a long shot, much hotter than Mercury, and we'll talk about why that is as we go through. Before we move on, though, we need to have a little discussion on how scientists measure distance in space. Scientists use what we call light years to measure long distances in space. And what a light year is just the distance that light travels in 1 year. Light is the fastest thing, right? Nothing can travel faster than light. And so if you were to turn on a flashlight, start the stopwatch, and a year later stop it, how long has that beam of light gone? Which is not super fair on Earth, right? The speed of light in a vacuum, we should be saying. And it's about 9.5 trillion kilometers, which is just a mind-bogglingly large number. But the distances in outer space, and we'll discover this especially as we move on to our next unit, when we talk about our galaxy and even the universe at large, that those distances are so huge. We need this mind-boggling number. 9.5 trillion kilometers is 1 light year to measure them. We can also measure distances in space in light minutes or light hours, which likewise is how long it takes light to travel. Not how long it takes, but the distance light can travel in 1 minute here on Earth, 60 seconds, or in 1 hour here on Earth. In our solar system, we tend to measure distances in what we call astronomical units. And an astronomical unit is just the average distance between the Earth and the Sun. And so we would say Earth is 1 AU from the Sun on average. So any distance that is less than 1 AU is a shorter distance than Earth is from the Sun. And anything that is larger is obviously a longer distance. And it's about 150 million kilometers. I feel like when I put big numbers on a screen like this, those numbers lose all meaning. But 150 million kilometers is roughly 1 astronomical unit, which translates to about 8.3 light minutes. That's how long it takes the light from the Sun to reach us here on Earth. So when you look, the light you see outside from the Sun took 8.3 minutes about to travel from the Sun to us. Here are other stars and astronomical features. Alpha Centauri is actually a cluster of, I think it's 3 stars, the closest of which is called Proxima Centauri. And Proxima Centauri is aside from the Sun, the closest star in our galaxy to us here on Earth. So it's like we have our solar system, which is made up of the Sun and an Earth, and then Mercury, Venus, Earth, Mars, and so on and so forth. All of that is in our solar system. The next closest star, other than the Sun, would be Proxima Centauri. So let's remember, Earth is about 8.3 light minutes from the Sun. Proxima Centauri is about 4.2 light years away from the Sun, which is again just orders of magnitude difference, right? If the light from the Sun takes 8 minutes on average to get to us, well, that light blows past us, right? The light from the Sun gets thrown past us, And in 8 minutes, it goes from the sun to us, and then 4.2 years later, it hits Proxima Centauri. Or think of it this way: if you pull out a telescope and you find Proxima Centauri and you look at it, the light you're seeing hitting your telescope left Proxima Centauri 4.2 years ago. You are looking into the past of Proxima Centauri. It is difficult to fathom these distances. They are so extreme, and these stars all look so close. Like when you look at a picture like this, all these stars look so close to one another, but they're not. They are incredibly far from one another. So let's just do a quick overview of the four terrestrial planets, starting with the first one, starting with Mercury, the closest planet to the sun. It has no moons. And it is about 1/3 the size of Earth, really roughly 1/3 the size of Earth. And Mercury, we saw in our overview slide a little while ago, rotates pretty slowly on its axis. It doesn't spin very fast. One day on Mercury, right, the time it takes for Mercury to spin is about 59 Earth days. So about 2 months is how long it takes Mercury to spin one time. And that means the side facing the sun has a lot of time to heat up, right? Like if it takes about 59 days to spin, that means the one point spends about 30 days facing the sun. Imagine if the sun were overhead your house for 30 days without ever going down. Things would heat up to pretty extreme temperatures. So temperatures reach about 427 degrees Celsius in the daytime on Mercury. This is a picture of Mercury passing in front of the sun. And you can see, I put this in here just because I want you to see the size, the relative size, how huge the sun is, and just how tiny Mercury is as it passes by the sun. Conversely, the side facing away from the sun, the night side on Mercury, has a lot of time to cool down. And no atmosphere means no greenhouse effect, means it doesn't retain heat like Earth does. We talked about this when we talked about the moon, right? Mercury is not that different from the moon. And so Mercury can get as cold as 173 degrees below 0 Celsius at night. Mercury has the largest difference, the biggest disparity between day and night temperatures in our solar system. So its hots are really, really hot. But because its colds are very, very cold, its average temperature is not as high as Venus, let's say. Mercury is the tiniest planet, the smallest of all 8. It's smaller than Earth. It has less mass, which means it has less gravity. So if you went to Mercury and you stood on the surface, you would weigh only about 39% of what you weigh on Earth. So if you are a 150-pound person, you would only weigh about 50 pounds on Mercury, which is kind of misleading. You wouldn't actually lose weight. You wouldn't be different. You would have the same body. It's just that Mercury's gravity pulling on you is less strong than Earth's gravity, and so you could jump higher. And you've seen the pictures of the astronauts jumping around on the moon, and how weird it is when they walk and they kind of take these moonwalky big bouncy leaps and stuff like that. It'd be similar on Mercury. Mariner 10 was an unmanned probe that visited Mercury back in the 70s, back in 74 and 75, and it mapped about 45% of Mercury's surface. And those images showed that Mercury's surface is pretty similar to the moon. If I showed you a picture of Mercury and a picture of the moon side by side, you might not be able to tell the difference unless you really knew what you were looking for. They're both pockmarked by craters and plains, right, from old lava flows. We think Mercury has a dense nickel-iron core and a zone of melted material in its interior. Again, I'm going to use the word think because we've never stepped foot there. We haven't done any drilling there, so we don't know for sure. But we believe, and there's a couple reasons we think that. To date, only Mariner 10 right, from the 70s actually landed on Mercury, but Messenger is another craft that's been orbiting Mercury since 2008, and it's been sending us photos and data and stuff like that. Um, this was a picture of the Mariner probe, Mariner 10, that went to Mercury. Some of the images from Mariner 10, and they look kind of pixelated, and that's because these are what we call composite images. You can see, especially over on the sides here, these like squares, and that's because Mariner didn't like zoom out and take one large picture of Mercury. It orbited pretty close. So imagine if you're trying to take a selfie, but you're holding the phone, a half an inch away from your face. You could still make an image, but you'd probably have to take about 1,000 pictures and then kind of put them all together to make an image of your face. And same idea here. We've got about 1,000 smaller pictures, all taken from a relatively close distance, and a computer program puts them together and gives us this image. Here's some more images from Mariner 10. Again, if I told you this was the moon, you'd probably believe me, because this looks a lot like the moon. The second closest planet to the sun is Venus. And it's sometimes called the evening star because it looks so bright from Earth. Venus you can see without a telescope even um, pretty often. It's not difficult to see in the night sky. Sometimes astronomers refer to Venus as Earth's twin because they have similar masses as we saw, similar diameters, similar densities. They're in those three ways they are relatively similar. And we also believe that the interior of Venus is pretty similar to Earth, that it has a liquid metal core and so on. This is a picture of Venus in the night sky, and I actually think that this one is Venus over here. I don't think it's one of the bright ones, but you might mistake it for a star, and it would be understandable if you did that because it kind of looks like it when it reflects the sun's light at night. It looks like a tiny star. The surface conditions of Venus, however, right? So we talked about, Earth's twin, Venus, but the similarities kind of end there because the surface conditions of Venus are very, very different from Earth. A lot of people talk about wanting to go to Mars and like set up colonies on Mars. Elon Musk is always talking about that. And you might be wondering, well, why not Venus if it's Earth's twin? Well, because the surface conditions are like wildly different. And the average surface temperature on Venus is 464 degrees Celsius. That is unbelievably hot. In comparison, Earth's average surface temperature is 15 degrees Celsius. The atmospheric pressure on Venus is much, much greater as well. Standing on Venus's surface would be like standing underwater at the bottom of the Gulf of Mexico. That's the pressure that would be pushing down on you. And we've had this conversation before. If you've ever swam to the bottom of the deep end of your, a pool or something like that, you feel the pressure in your ears. It's noticeable. Well, now imagine swimming to the bottom of the Gulf of Mexico. It would crush you. Your body wouldn't be able to stand it. And that's what the surface of Venus is like. Venus's atmosphere is mostly carbon dioxide and nitrogen. Carbon dioxide is an incredibly efficient greenhouse gas. Whenever we're talking about carbon emissions and things like that, when we did our environmentalism unit, that's carbon dioxide. And Venus's atmosphere is a lot of carbon dioxide. So like Earth, it has a greenhouse effect. But because of all that carbon dioxide, it actually has a much, much stronger greenhouse effect. And so for that reason, it is the hottest planet in the solar system. And it's something that should make us, frankly, a little bit worried, right? That because, it's one of the reasons we understand carbon dioxide to be such a great greenhouse gas, is because we see the effect it had on Venus. Liquid water cannot exist on the surface of Venus. It would evaporate instantly. It just can't exist. Earth's clouds, the clouds, right? We studied them when we did atmosphere, are made of water vapor. But Venus's clouds are made of sulfuric acid. It rains sulfuric acid on Venus, which is pretty nasty. So these clouds, these like yellowy bands you see, these clouds in Venus's atmosphere. This is not from the surface. This is uh, orbiting Venus. This is a picture taken from like the upper atmosphere of Venus. Those clouds are sulfuric acid. Sulfur is a yellowy element, so that's why Venus looks yellow, because of those sulfuric acid clouds. It was the U.S. orbiter Magellan that mapped the surface of Venus with radar waves. And Magellan's radar, again, a classic example of remote sensing. We can't just look at Venus because you can't see through the clouds, but their radar was able to penetrate that atmosphere and actually see a surface that had very, very few impact craters. Earth's atmosphere burns up most of the space debris that enters it before it ever even hits the surface. Very, very, very few things make it through Venus's atmosphere. Sulfuric acid burns up a lot of stuff. One day on Venus is 243 Earth days in length, which is just a fun fact, not really connected to much else. Radar measurements revealed that Venus rotates clockwise, whereas counterclockwise is like the normal way of rotating. So it rotates backwards, basically. It orbits in the same direction as everybody else, but rotates backwards. We would say Venus is in retrograde rotation, and most other planets are in what we would call prograde or counterclockwise rotation. This is an image taken from a probe on Venus's surface. This probe, I think, survived on Venus's surface for a couple hours before it just overheated and was destroyed. But it sent us back these fascinating photos showing us a rocky, desolate surface of Venus. These are some of the radar mappings of Venus's surface. Again, from that Magellan spacecraft, the radar was able to penetrate the sulfuric acid clouds. And just some nice pictures of Venus. It looks pretty scary. I wouldn't want to go there. Then there's Earth. Earth, third planet from the sun, fifth largest in the solar system. It's the only planet known to support life, not just in our solar system, but anywhere. Our distance from the sun and the fact that we are nearly circular, we're still elliptical, but nearly circular orbit, keep our temperatures within a critical range. We are not too hot, not too cold. Scientists refer to this as the Goldilocks zone, which is kind of a silly, childish thing to call it, but that's what we call it, the Goldilocks zone. Earth is warm enough so that most of its water does not freeze, and yet it is cool enough that our water does not completely evaporate. Liquid water can exist on our planet, and liquid water is on our planet in abundance. It covers about 71% of Earth's surface. Almost 3/4 of Earth's surface is covered in liquid water. And that water is a key factor in the development of life on our planet, and it's the reason why scientists look for liquid water on other planets as a sign that they might be hospitable. They might be able to sustain life. And based on what we know, Earth is the only planet with liquid water at the surface. Earth and its moon. Earth's atmosphere, we talked, is mostly nitrogen and oxygen. That's another huge factor that has enabled life to exist on our planet. The greenhouse effect keeps us warm enough to support life. We do not freeze at night because the greenhouse effect keeps us warm. We have a magnetic field that deflects harmful solar radiation. Earth, there is truly no place like it. Let's talk about Mars. We spent the whole unit on Earth. Let's move on. Mars, fourth planet from the sun, sometimes called the red planet, And that's because its soil has a lot of iron in it, and iron, when it rusts, is reddish, and so Mars has like this reddish color to it. There are lots of strong winds on Mars, and there are these frequent dust storms, these like red iron rusty dust storms on Mars. Mars has a longer year than Earth. It's further from the sun, and so it moves more slowly in its orbit. It takes 687 days for Mars to orbit the sun, and again, super roughly, it's about 2 years on Earth. So every two times we go around the sun, Mars goes around once, basically. And Mars is much smaller. It's about half of Earth's diameter, and it's got less gravity for that reason, less mass, less gravity. So Mars's gravity is about 39% of Earth's. Mars has two moons, Phobos and Deimos, and they were probably at one point they were asteroids that were captured by Mars's gravity. So we know that the asteroid belt is between Mars and Jupiter, and so every once in a while, when Mars gets a little close, it's theorized that it picked up two uh, rocks, two asteroids, and they ended up being the moons. Phobos. So, if you're familiar at all with mythology in ancient like Greek and Roman mythology, most of our planets are named after Greek and Roman gods. Mars was the god of war, and the red, they called it that because it was red, and red reminded them of blood, and they called it the red planet. Phobos and Deimos are the Greek gods of fear and dread. So Mars, the red planet, the war god, has two moons, fear and dread, which again sounds pretty terrifying. Here's a picture of Mars. Again, you can see that rusty red color covering most of it. And here are Phobos and Deimos. These oddly shaped. They're smaller than Earth's moon, and they are much less spherical. They're not perfect spheres. They're not round. They're kind of weirdly shaped. Phobos and Deimos. Mars's atmosphere is not that dissimilar from Venus, but there's much less of it. Mars has less atmosphere than Venus, which is actually a good thing. It's got a weaker greenhouse effect, um, and so and no sulfuric acid clouds, which is kind of cool. Mars has a lot of topographical features, like it's got mountains, volcanoes, canyons, valleys, craters, a lot of the same stuff you would find on Earth. The tallest mountain on Mars is taller than the highest mountain on Earth. It's 26 kilometers high. It's called Olympus Mons. It's an extinct volcano that, again, is taller than Mauna Loa, which is the highest volcano on Earth. It's only about 9 kilometers. So Olympus Mons is about 3 times higher than the highest volcano on Earth. And this is a picture of it. Again, this is the vent cap, and you're seeing just the color. It's just, you can see the curvature of Mars behind it. It takes up like an entire face of Mars. It's huge. Mars's thin atmosphere, combined with its distance from the sun, makes it cold. But it does have seasons because it has a tilted axis just like Earth. It's just that all of the seasons are colder. There is frozen water on Mars. It's got an ice cap in the north, but at no point does the temperature get high enough to melt that ice. So no liquid water on Mars. We've sent many rovers to Mars. They continue to photograph its clouds and land features and stuff like that today. And they also analyze rock and soil samples as they travel over the planet's surface. And they're constantly sending data back to Earth. This was the Mars rover. It's actually, it stopped working. Poor guy. But they kind of, like, they almost like anthropomorphized it. Like, it looks like a little creature. Um, but yeah, he roved around Mars's surface for a long time before his wheels finally broke and he stood still for a while. And then it was just a couple of years ago where he finally just stopped working completely. Um, yeah, the Opportunity and the Spirit probes. This is kind of a timeline. You can pause if you want to read through it. There's some interesting stuff here about the different discoveries that these two rovers made as they swept over Mars. You can see the tracks that this rover made, and I guess he got a little crazy at one point. He was traveling pretty straight and then went a little wonky. But yeah, that's Mars. Fun fact about the Mars rover: the antenna on the Mars rover you can see in the picture here was designed by Bill Nye the Science Guy, and he designed it to be a sundial. So based on the orientation of the rover and the way the sun is hitting it, they can visually see what time any of the pictures were taken. Bill Nye the Science Guy designed the antenna on the Mars rover. Fun fact. Your homework's the next page in the packet. Thank you so much for sticking with me on this slightly longer than average video, but I'll be in touch soon, guys. Have a great day. Bye.